Hello. You sprung a leak, Andrew. Alright, so today we're going to be looking at variation of parameters. So last time, in the lecture sense, we actually proved all of this. We derived this technique for solving any second-order linear constant coefficient inhomogeneous equation. We sort of said, well, undetermined coefficients only works for certain right-hand sides or certain forcing functions as g of t, and we want a more general method. We hypothesized that this would be an appropriate solution. That is, we took what we would normally write down as the solution of the homogeneous problem, and instead of saying a and b are arbitrary constants, we made them some unknown function. We then derived, we had to place another condition upon a and b, but we don't actually, that's no longer relevant because we've used that condition to derive the following expressions for a and b. So the a is this awful integral thingy. We've got a w in there, which is called a Wronskian. B is the same thing with the other elementary function, and the sign changed. All right? The Wronskian is essentially a determinant. Right? So if we look at that, it's a determinant of the elementary solutions. So y1 and y2 are what we would normally ascribe as the solutions of the homogeneous problem, without the arbitrary constants. You can leave the arbitrary constants in there if you wish, it'll just make a mess. Right? They'll pan out in the end. Alright? So a couple of points on this. I'm sure you're all very keen to memorize these things. I wouldn't bother memorizing because it's reasonable to provide it. Right? I don't want you making mistakes due to a poor memory. What I would point out, to help you remember and not make transcriptional or silly errors, A is associated with y1. A uses y2 in the integral. Okay, so that's a bit of a memory trick to help you work out what you're supposed to be doing. And B is the opposite. One of these has a minus sign. I don't actually think it matters which one. I think it all pans out in the wash if you swap the signs. But just be careful, right? Use this form. What might happen is if you swap the signs, you have to swap the determinant around. You can eat it like that. Okay? So that's just how this version pans out. Again, if you're looking at a different textbook, perhaps they've worked it through using a different convention. I don't know. I've only ever seen it like this. Right? Because this one fits with my muscle memory of writing these down from when I was a kid. All right, so essentially today we're going to go through a bunch of examples. How long does it go for? About a minute? No, we'll have a lecture. Yeah, it is. I was wondering what you're giggling about.
Alert! 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 Alert!
This is supposed to happen at 7 in the morning. Some fucknugget down at Duntroon has decided to push the button now.
Alert! Alert!
Yeah.
Alert! Alert! Alert!
Plus I just... I'll yell at them first, rather than just literally sit down, and then you can go out. Jason Sharples had a major in his lecture, and Jason chewed out the students for talking too much during the lecture. Please experience. Old mate Major got up. Alrighty, I'm sorry about the interruption. That's a cabbage down at Duntroon. This time, we will look at examples of how to solve problems with the method of variation of parameters. Where was I? I told you you didn't have to memorize it. It will somehow be given to you. But just remember this form so you can keep track and not make silly errors. All right, so some of you would have had a tutorial yesterday, notionally. So you've missed that tutorial. One of the examples today is drawn from that tutorial. One of the examples today is drawn from an example that I presented in my tutorial as well. Right, so some of you may have seen a couple of these examples, may have even worked through it, but for the rest of you, they haven't. One of the other examples is a more tedious, or it has some interesting features. And what I'll do is I'll compare a couple of these to what we would get if we solved with variation, undetermined coefficients. So we're just going to learn the steps first. So a fairly simple idea. Right, so this is a very simple example. Most of you should be able to crank through it by undetermined coefficients, and in fact that's an easier way to do it. But what we're going to do is we're going to apply variation parameters. Again, we need our y1 and our y2, which are the parts of the solution of the homogeneous problem. So we're going to solve the homogeneous problem first. I'm going to belt through that really quickly. All right? So what we would normally write is this, right? That would be our normal solution of this homogeneous problem. Okay? Now, what I tend to write instead is that, right? I tend to go, instead of writing down the homogeneous solution, I write down y1 and y2 directly. Note that y1 and y2 do not carry constants. Right? They don't have that arbitrary constant floating around. Now you got a choice here. I don't care if you write this down and then jump to a and b are functions. Right? Provided you still correctly identify the y1 and the y2, because you need to correctly identify them in your determinant, right? Your Wronskian. All right, so I'm not fussed how you get there. It's just that this is the y1 and that's y2. If you pick them the other way around, doesn't make a difference. You're just going to flip your determinant around. You've just got to keep your reasoning throughout consistent. And at the end of the day, you might get A, your A might be my B, for example. Right? Don't care. When you write down the final answer, it'll all pan out in the wash. Okay? So don't worry too much about making sure that one's A and one's B. Just keep everything consistent in your solution. Right? And that's what I mean about when you look at the A here. A is associated with y1 in the answer, in the solution. A depends on y2, right? So that's how you keep your answers consistent. And you've got to swap things in here, right, if you end up with them the other way around. It's not going to make a difference. It'll all fall out in the end. Okay, but now we've solved the homogeneous problem. Step 2. Let's just calculate the Wronskian. It's a determinant, and it's got a formula. Okay, so you can kind of remember it as the first. I remember it as y2 prime as the first thing I write down. Then the next component of that determinant will be the other function, not differentiated, so y1, minus the other term in the determinant, so y2, y1 prime, right? So you swap the prime. That's just how I remember it. You might come up with some other mnemonic, or you might just rely on the formula sheet. Okay? If you're relying on the formula sheet, make sure you copy it correctly. What happens with Wronskians is that typically they do something nice, at least in these examples. They will boil down to some simple, nice function that is easily manipulatable. If you end up with some awful-looking sum of different terms, you may have stuffed up, right? It's not necessary, but it's an indication that you've missed something in the problem and it's no longer falling out in the nice, neatly engineered way, right? So that's an exam tip. It's not necessarily going to be a real-life tip. But you've got to remember, right? The solutions for y1 and y2 are either exponentials with different indices, so they should multiply out and become the same thing, right? Because you've got the product of two exponentials. You've either got sine and cos, which will become sine squared plus cos squared, which is a trig identity, and you can pull it out. Yeah? Because it's the determinant, right? You differentiate one, you're going to get the same as this one with a different sign. Sign's there, right? So we've got the sign change in there. So if you've got trig roots, this thing's you're going to use the trig identity, sine squared plus cos squared equals 1, right? That's the only, I think, the only possibility here. Third one is when you've got the t, e to the t, and that's the one that gets messy. All right, because you've got to do this, you've got to do one of these derivatives by the product rule, but it should still collapse into something like t plus something times e to the something, right? Because remember that e will be common. All right, so it should sort of mince down into something relatively polite. All right, so that's our Wronskian. And in this case, it is y2 prime. So that's minus 3 e to the minus 3t minus times e to the minus 2t minus 2 e to the minus 2t e to the minus 3t equals, you'll find that that's minus e to the minus 5t. One of the things that I find the most difficult and tedious about these things is keeping track of all the signs. I love making sign errors. It's a real nuisance. Be very careful. So that's our Wronskian. Step 3. At this point, it's mechanical, right? I'm just cranking the handle through my different formulae. And I'm just dropping the t's for convenience. Okay, so notice how I've turned the e to the minus 5t on its head. I've used the index laws to change that minus to plus. Yeah? Happy? y2 was, be careful, e to the minus 3t. That's the other popular mistake that I make, at least, is I confuse the y1 and y2, and then I start muddling things up. It's very annoying. A and b shouldn't really be equal. Right, that's a bit odd. I guess it's possible, but it doesn't feel like it should be likely. G of t, in our case, it's the right-hand side, it's just t. Yeah? So we recall that from the original problem. Awesome. We've boiled this down to an integral that we now can do. How do we do it? Yep, it's by parts. What do we choose as the function to differentiate? What we would normally call u. T, because it's polynomial, it becomes simpler when we differentiate. So, integral of u dv, I'm just reminding everyone here. Alright, that's the notation that I prefer. So I'm going to let that equal u, so that's dv, implies, I'll write it out. Yo. It is meant to be e to the 2t. Thank you. Okay, so that's our integration by parts formula bit. Right, so now we can work forward. This integral is then equal to t on 2 e to the 2t minus integral e to the 2t, there's a half in there, dt, so that's equal to t on 2 e to the 2t minus half, quarter, 1/4 that, and what else? Classic constant. Yes, I've called it C here. Alright, so that's cool. Actually, I've called it D here for some reason in my notes. So let's just go with that. Oh, I see. Yeah. Okay. So remember the constant of integration, because that's where it pops up. Right? We don't impose an arbitrary one anymore at the end of the solution. That's where it explicitly arises when we do that integral to find A and find B. So, same method. Except now we end up with okay, so our y1, we scroll back up here. We see that y1 was the one with the minus 2. Alright, so that's what we subbed in. Our g of t doesn't change. All right, so I kind of belted through that a little bit, but look at the form of a and b. Right? They're nearly identical apart from a minus sign and the different function. So I know that I should be getting a very similar looking integral. That's a bit of a check on my working at the moment. So y1 is that. Wronskian doesn't change. Remember that I've just flipped it on its head. And I've got a minus sign out the front. So is everyone happy? All right. How can I cheat and do this integral really quickly? Wolfram alpha is not allowed. That's the same integral, essentially. There is a difference in sign and a difference in the constant in the exponent. Yeah? So all I'm going to do is I'm going to pretend, so here I get a factor of a half, here I would expect a factor of a third, right? So I'm going to cheat, and I'm going to carefully transcribe this, changing all the all the 2's to 3's. I've still got a minus sign outside, yeah? So that's a 2 squared. So this is a 2 squared. Remember, we got it because we did it twice. E to the 3t plus c. Yeah? Yeah, we integrate twice, we pick up the factor twice, so it's squared. Yeah? Happy? I mean, you can work through it. I'm just a bit pressed for time. So, now we've got all our ingredients. We've found our A, we've found our B, and we know our y1 and y2. So it's just a case of putting it together at the end. So what number step is this? 4. Oh, thank you. Oh, did I copy my pattern wrong? Yes, I did. Thanks. So now I've just got to assemble these bits. So I've got this bit here. I've got this bit here, and I've got my y1 and y2. So I'm just going to copy that down. So this is my A. I'm going to be naughty. Why have I been naughty? That looks like a sign error on my C, yeah? C is a constant, an arbitrary constant. If I multiply it by -1, it still remains an arbitrary constant, yeah? You can eat factors into C, as we'll see later, and we can eat minus signs. I could do this, right, and put an explicit label on my original constant and then C equals minus C1, for example. Yeah? That's really what I've done. Okay, so that's carefully keeping track of my y1 and my y2. Yeah? Alright, this thing simplifies out beautifully now. I've got a 2t there and I've got a minus 2t, got a 3t, minus 3t. So let's simplify this. I'm going to have a t on 2, and then I'm going to have a minus t on 3. I'm going to have a constant term. I'm going to have a minus 1/4 plus 1/9. And then I'm going to get d And this all comes out to be that's a plus if I remember. No, it's a minus. A half minus a third. All right? So that's our general solution. Are we happy? Why does that look like something we expect? What does our intuition tell us? That would be what we would normally call a homogeneous part. This looks like C1t plus C0, the same thing that we would get if we used undetermined coefficients. So let's have a bit of fun and try and do it by undetermined coefficients, knowing so we don't have to begin very much at the beginning because we've already solved the homogeneous problem. It's a polynomial right-hand side, so that's what we'd guess as our annihilator function or our particular solution or particular integral. And now we just go through the process. Because it's a polynomial, it's very straightforward. What's my equation? Plus 5yp prime plus 6yp equals t. All of that boils down to 5c1 plus 6c1t plus 6c0 equals t. Now we equate terms. So we equate the t term very clearly. 6c1t equals t. c1 equals 1 over 6. We've got a 0 constant term, so when we equate the constant term, we have 5c1 plus 6c0 equals 0. Oh, why is that yellow? Then c0 equals minus 5 over 36. So if we were to compare this with our previous solution, right there, we're actually quite pleased with ourselves because we've discovered the same answer, as we should, right? These solutions are unique, there's no difference between them, and that's where we should get to. Alright, so is everyone happy with that? Alright, so you'll notice that it's quite a tedious process. That was about 20 minutes going through it slowly, right? I can probably do it in 10 to 15 if I'm quick, but it's long, right? So the expectation is for you guys that this type of question will take you a long time, especially if I then give you initial conditions that you've got to sub in. So think about that. If you're given this type of question in the exam, think about budgeting your time appropriately, right? Because this is a lot longer, right? It takes like 2 seconds to do undetermined coefficients, but to go through all those integrals by parts, in this case, right, where we've got a polynomial right-hand side, it's very, very long. If I just give you an equation, tell you a polynomial right-hand side, you probably should choose, if you're given the freedom to choose, you should choose to use undetermined coefficients, because you'll get the same answer a lot faster, more efficient, right? If I tell you to use variation of parameters, then you've got to use variation of parameters, otherwise you don't demonstrate your knowledge, okay? I might tell you to do it both ways. compare the answer. That would be kind of cruel. No, you're going to get tested on variation of parameters. Otherwise, I wouldn't be here. Like, I could be somewhere else. Are they open? All right. Just in the interest of time, because that was a bit long. All right. So, second example. This one's from Tute 6, but probably not many of you, unless you've looked at it in your own time, got up to doing it, even if you had your Tute yesterday, if you actually had a Tute this week. This is the example. It's a bit ugly. We notice that we've got a product on the right-hand side, so we're thinking that undetermined coefficients might be a bit of a nuisance. Secondly, this lecture is all about variation of parameters, so let's try that method first. So let's solve the homogeneous problem. Okay, so again, doing this fairly quickly now, just going straight to the characteristic equation and then going straight to the roots of that characteristic equation. Oh. Yeah? Right, that's the solution of our homogeneous problem. Okay, so again we'd identify this as y1. That's just how I'm going to do it, and we're going to keep that consistent. So if we proceed with variation of parameters, we would calculate the Wronskian first. Okay. Again, it's an exponential Wronskian, so it's nice in the sense that 3e to the 2t minus minus 1. Okay, so that's doing it a bit quickly, but I'm just keeping track of all my indices. I'm just differentiating to get the different constants, yeah? We happy? Next step. Is that. Why is it that? That's 1 over w. That is y2. And that bit is g of t. We all happy? And I've got my minus sign. It's a very small minus sign. Let's make that minus sign bigger. That just pops out of the integral. Conveniently, minus 2 plus 3 minus 1 is 0. So in this case, our a function is very straightforward. We happy? No, it's not, sorry. Let's just make sure. I think that's a writing, yeah, that's a writing error this time here. Yep. Yeah, sorry, I know it's a change in the question, but I slipped up. I forgot to write it. Okay, so now B. So this is going to boil down to a t e to the minus something, or e to the something integral. 2 minus 2 minus 1 minus 1. That looks like that. Yay. And again, we're doing this by parts. Alright, so I'm still keeping this 1/4 out the front from my original integral. I'm going to now just do this integral, the final bit. Okay, we happy? Right, so now we've collected, so there I'm eating my 1/4 into my d. Again, it's just a constant, so 1/4 of d is still a constant. Again, I could do this and then go d equals d1/4, for example. Have I got my signs all correct? No, naughty. Happy? So, last step, put all this together. In the interests of brevity, so I've taken my A and I've multiplied it by my Y1. I'm now going to take my b and multiply it by y2. Remember that y2 is like 3t. That's what we would normally call our homogeneous solution. That's a bit unusual, but that's the rest of our solution. Okay, so we can group this up a little bit more. We can make it look nicer. Okay. So there, I've noticed that I've got a factor of e to the t that I can simplify. I've somehow generated a minus 1 over 64 e to the t. I've got a c times e to the t, or e to the minus t, sorry. I note that c, an arbitrary constant, minus 1/64, is still an arbitrary constant. So I have eaten my arbitrary constant. If you wished, you could stop here. That's perfectly acceptable. But when you do your undetermined coefficient solve, you may find a bit of a surprise. So, undetermined coefficients, we know our homogeneous solution. We would guess for y particular c2t squared plus c1t plus c0 That's one too many t's. No, it's not. E to the minus t solves this problem, yeah? So we're going to have a problem where we've got to multiply by t squared. So we're actually going to take the higher order polynomial. No, you don't need c0 there anymore. So, okay, so firstly, if you did guess that, like I did in my answers, in my previous one, you would find c0 would be arbitrary, which is what I found, right, when I plotted through this. And that's perfectly okay because you get the factor of c0 still floating around, e to the minus t, gets eaten at the end by the arbitrary constant big C. Right? What we've got, or what we notice, is that our normal guess, our naive guess, would be c1 e to the minus t. Yeah? We've got a first order polynomial times e to the minus t. What's wrong with that guess is we're substituting e to the minus t into in our particular solution. e to the minus t solves our homogeneous problem. So we're going to find a resonance case. This is all going to fall to pieces and we're not going to be able to solve it within undetermined coefficients. Multiply by t, right, to get us out of trouble. Or alternatively take a second order polynomial guess. Actually, I'll leave that. Yp prime equals I'm going to have to rush through the rest of this example now. Okay, so that's product rule. Differentiate the exponential, leave the polynomial alone. Leave the exponential alone, differentiate the polynomial. Now we do it again. Heaps of times. Actually, no, I can avoid doing it. No, it's just easier. They're the same term, they've got the same sign, and so they should add up. What, sorry? Comes from here. I differentiated the exponential here to get that minus sign. Then I've got a plus, I differentiate my polynomial. Now that's plus. Happy? Alright. Sub into y particular double prime minus 2yp minus 3yp all of this boils down to, and now I'm really skipping steps because I've got a minute left. So it does collapse quite a lot. We then find, by equating like terms, so where's my t e to the minus t here? It's the